are starting at the absolute bottom of the cosmic ladder. Down here in the microscopic void, an average virus measures roughly 1 × 10⁻⁷ meters across. Pulling back just one stop, we hit a bacterium. Its width is roughly 2 × 10⁻⁶ meters. To find out exactly how many times bigger we just jumped, we have to start with the first step of our method, checking the exponent. This can be a trap because a larger negative number feels like it should represent a larger value. Instead, think of negative exponents as depth underwater. A value of 10⁻³ is closer to the surface, a larger physical value, while 10⁻⁸ is deeper and therefore smaller. Using that logic, the gap between a bacterium at -6 and a virus at -7 is exactly 1. That single jump gives us a base multiplier of 10. To finish the calculation, we divide the front digits. 2 divided by 1 is 2. Multiply that by our base of 10, and we find the bacterium is exactly 20 times wider than the virus. By treating negative exponents as depth, the math reveals why a bacterium completely dwarfs a virus. We can apply this same scale to ourselves. Zooming out from the bacterium to a human figure, we hit a new baseline, 2 × 10⁻⁴. The gap between exponent 0 and -6 is 6. That tells us a human is roughly 1,000,000 times larger than the bacterium. At this scale, the front digits barely change the story. Even though both numbers start with a 2, the exponent gap is what defines the massive difference in size. This happens because of a mathematical guarantee. Even the highest possible number at one exponent, like 9.99 × 10⁻³, is still smaller than the smallest possible number at the next exponent up. Checking the exponent first isn't just a shortcut. It's a rule built into how these numbers work. There is no gap left for the front digit to close. Moving beyond the human scale, we pull back to find the Earth, which has a mass of 6 × 10⁻⁴ kilograms. Continuing outward, the Sun fills the view at 2 × 10⁻³ kilograms. To find the jump in size between the two, we look at the gap between 30 and 24. That's a difference of 6, ballparking the Sun at 1,000,000 times heavier. For the precise ratio, we divide the front digits. 2 divided by 6 is 0.33. Shifting the decimal to normalize the notation, 0.33 × 10⁶ becomes 3.3 × 10⁵. In standard form, that means the Sun is roughly 330,000 times heavier than the Earth. The same three-step method works at the scale of the solar system just as easily as it did for microscopic cells. Crashing back down to the surface, we can use this to compare human populations. The US population is roughly 3 × 10⁸, while the entire world is about 7 × 10⁹. With a gap of 1 and 7 divided by 3, resulting in 2.33, we can see the world population is about 23 times larger than the US. To see if the method has clicked, try these 4 comparisons. You can pause here to work through them yourself. For the first two, the exponent tells the whole story. 7 is greater than 5, and -2 is less negative and therefore larger than -5. For the star, the exponent gap of 3 means it is 1,000 times farther away. And for the last set, we simply order them by their exponents, -4, then 0, then 4. The exponent identifies the size. By checking it first, you can accurately compare the scale of anything in the universe.